Good afternoon. So, what we thought to do basically, our live is a discussion a little bit about the topic of this particular week, which is regarding the interferometry. So, we have already discussed earlier that if you remember, yeah. So, if we have a single dish, which is kind of has a diameter of d, okay, total. Then for a single dish, the resolution of a single dish is proportional to lambda by d. But what happens is that for lambda by d, if the lambda starts increasing, then d also has to increase to keep the resolution same. Now, for very, very, very low frequencies or very large lambda, what happens is this d becomes very large, and impractical to construct such a large telescope. So we have given the comparison that supposedly for a green bank telescope. So a green bank telescope has a diameter is a diameter of 100 meters. Supposedly, it was operating in lambda of 1 centimeter. Then the resolution of the same will be lambda by d, which is 0.01 centimeter over 10. So roughly of the order of, we can say, 10 to the power minus 4 radians. Now, if I now looking at lambda of 1 meter, which is corresponds to frequency of 300 megahertz. If I compare to that, then what happens? I have to make a dish to keep the resolution theta same. I have to make a dish which is, so 1 meter is like 100 times larger. So I have to make a dish which is 100 times larger than 100 meter. That becomes 10 kilometer. That's more or less impractical or not feasible to be made. Okay. So that was the reason why we need to have more, some different technique, different, method to go about doing this, because the resolution has to be, cannot be compromised. So what we introduced is something called an interferometer. So let's talk about that. So so for an interferometer, what happens is we replace a big dish. Suppose this was a dish. Instead of having a single dish of diameter d, we break it up into smaller dishes of smaller diameters. Okay. So, so supposedly we have n number of small dishes, and we break it up into the smaller dish diameter of d, And this is our total collecting area for the small number of dishes. So this should be balancing the total area which is done by the bigger dish. That's roughly. So it cannot be exactly equal, but roughly. So what happens now? We replace that with some smaller dish. We showed something like a VLA or a GMRT, and so we have this kind of a white kind of an kind of configuration. And so what happens is now the maximum baseline, the maximum baseline between any two antenna, that is now considered for the resolution. So my resolution element now is proportional to lambda, the wavelength, over maximum baseline. So that becomes much easier because now the individual antennas can be built of a smaller diameter D to roughly match this kind of a thing. So if we do not want to compromise on the collecting area, then the collecting area is kind of proportional to the geometric area, D squared over 4. And I have n number of dishes in the entire array. And supposedly the n is 30 or 27. So I can calculate what kind of a smaller D I can live with, which will be much, much smaller than this capital D of 10 kilometers, even if we go with the previous example. So this maximum baseline kind of replaces the resolution element. Okay, so that really saves the day for us, and we can still operate with smaller number of dishes, smaller size dishes, and large number of smaller size dishes, and kind of still do something called interferometry. Okay, that was explained in the last week, and we went from there. Now, what happens? How do we operate such a something called the interferometer? That's the next question. Let us look into that. Any questions so far? We are doing this live because we wanted to have reactions. Anyone hearing us? Asha, am I audible?
Yes, sir. You're audible.
I can hear you.
Anyone? Okay, doesn't look like anyone is here. Okay, so basically we started off discussing two antenna, antenna 1 and antenna 2. They are looking towards a source in the faraway sky, and which was sending this spherical waves, which after traveling infinite distance gets approximated to plane waves. Okay. Now, if I want to sense or detect the signal from a particular wavefront, then you can see, depending on the direction of arrival, the signals from one wavefront reaches one of the antenna earlier than the another one. Okay, so that will always be the case. So this difference in supposedly, if you just keep drawing this, and at some point it will be coming and getting sensed here. So if I kind of draw this okay, then this distance between the two antennas is B, and this angle of arrival of these waves are kind of theta with the zenith of the antenna. And so this additional path length, delta x, is given by, we have done it in the last class, B sine of theta. Okay. And if I want to change this into the additional delay time, this is B sine theta over C. Okay, why C? If you do the math, this additional path comes out to be B sine theta. You can go back to the previous lectures. And so you can see this is the additional path. Additional path is given by delta x, B of sine theta. And this is given by tau. Now, if I take this particular direction as S unit vector towards that, then this can also be taken as B dot S divided by C. Okay. So that's what we discussed last time, that this is what the difference between the both of the time delay between the signal appearing in antenna number 2 versus antenna number 1. All right. Then what we discussed was that there was output coming out from both the telescopes. So if I have taken the output from this antenna and from this antenna and did a multiplicative multiplication of both, so this is V1 and this is V2, then we will have the output. You can refer to the previous class notes, and you will see that the final expression comes out. Just give a second. Yeah, so if I get the two voltages, then if I just simply do V1 V2 the multiplication, then finally I get let's first do this. Just simply multiply. In the notes, we have used the symbol E, so that's fine. This gives us something like a V0 square cosine of 2 pi nu t times cosine of 2 pi nu t plus tau. Okay. So if I apply the cosine addition, then I get the first term to be cosine 4 pi 2 nu t plus 2 pi nu tau and plus v square by 2 cosine of 2 pi nu tau. Okay, that's the final output, because you can use the rule of the cosine addition, and you can finally get this as equal to this. Now, supposedly we get this term and we want to average this output, the multiplicative output, over time. So if you keep adding this particular function, then this is like a cosine function, right? So for a cosine or sinusoidal function, this is a time varying part. So if you average over a large time scale, this term goes to 0. So in this expression, we have 2 terms containing tau and 1 term containing t. So this expression over here is going to, for a given large amount of time averaging, this will go to 0. So what we are left with is nothing but this v0 squared by 2 and cosine of 2 pi nu tau. Okay, that's the output of a simple multiplying interferometer. Now, there are different kinds of interferometer, but we just wanted to restrict our discussion currently to this because it's a bit difficult to understand because we have a variety of students joining this particular course, and we would like to take it a little bit slowly. That's okay. So we did that, and that's where we kind of stopped last time, a little bit more. Let us go a bit further than that. So what else we did? We did, so again, if you draw that like a Y shape, right? And you have, instead of having, you have the dishes located at different points in that Y. That's a standard interferometric setup, both for 2 telescopes we have seen so far. So these individual circles are the dishes, okay? And so they are placed like this, and the distance, any 2 distance is the baseline. So how many total number of baselines can be possible? Supposedly you have n antennas, then nc2 number of baselines are possible. So we did this calculation also last time. Supposedly VLA has 27 antennas compared to GMRT, which has 30 antennas. So number of baselines, say given by NB for GMRT, is something like 13 into 29. And for VLA, this is nothing but 27 into 26 divided by 2. So this becomes 27 into 13. And this becomes 29 into 15. This is about 351, and this is about 435. Okay, that number of baselines. Now, if I look at it, this particular, in the previous slide, this particular output is between any two pair of antenna. Any pair of antennas, sorry, not any two, any pair of antennas. So for each of these baselines, we will have an output of, now I'm generalizing, instead of saying V1, V2, which I did last time, the expression came out to be V0 squared over 2 cosine of 2 pi nu tau, right? That was the expression we got last time. Correct. Now, if I do now generalize 1 and 2, I replace that with something called I and J. Okay, where I and J are any two antennas. This can be anything arbitrary among this 27 antennas for VLA or 30 antennas for GMRT. So if I do that, the Vij I can come out to be is equal to this cosine of 2 pi nu, and we have tau. So tau is nothing but, what was tau given earlier? Tau is B of sine of theta divided by C. Okay, so we can say this is nothing but B of sine of theta divided by C. Now, which B? What is the B? For the previous one, B was basically nothing but the distance between antenna 1 and 2. So for this one, we are having any antenna pair. So this is Bi, comma J. Okay, so that's the whole trick. So for any pair of antennas, for any pair of antennas, this particular term is becoming Ij. Okay, so if I just reword it this one, so Vi Vj is equal to V0 squared by 2 cosine of nu divided by C is nothing but two pi over lambda B of Ij sine of theta. Okay, so this is a very important expression. So for any two pair of any pair of antenna with corresponding to, there is a fringe rate which is proportional to the length of the baseline. So for any given baseline, you have a corresponding fringe. Okay. Now, if another thing we can understand, supposedly we have, it's very easy to understand. Let's just try to do this. Supposedly, let's go to the next slide. Supposedly you have two functions, right? Okay. And I say there is another function which goes as Okay, two function. So if I say the angular frequency of this is omega 1, and for this is omega 2, which one is greater than the other? So functions are nothing but cosine of omega 1t. Another one function is cosine of omega 2t. Say, and omega 1 is for this one, and omega t is for the other one. So it is very natural that omega 2 is greater than omega 1, which is rapidly varying. Okay. Similarly, we also got this particular function vi vj is now proportional to v0 squared divided by 2 cosine of 2 pi over lambda bij sine of theta. Okay. So as the bij increases, this is similar to this omega 2 is greater than omega 1. So this fringe spacing will become much more rapid. So the fringe function will vary more rapidly than if the bij is smaller. So for a larger baseline, this fringe function will have a much rapid variation for a small than over a smaller baseline. This again, we will come and talk about it in the next classes. Okay. So you can imagine that you have n antennas in an array, which gives to n b number of baselines, which is nothing but n antenna into n antenna minus 1 divided by 2, those many baselines. So we have those many number of these fringes for a given time. Okay. Why time is important? Because all this entire figure we have drawn for a given radio source and looking at this direction, right? But the source is not fixed. With the motion of the rotation of the Earth, the source is going to rise in the east and set in the west. So at some point, the source will appear in this direction. Then the antenna will be looking in this direction. So as the previous in this blue case, in the case of the blue, it was appearing first in antenna number 2 and then in antenna number 1. So it appeared here first, then this one. But in the case of right now, it will appear in 1 earlier than 2. So that's why this tau, you remember in the first slide, the delay is nothing but the dot product towards the direction of this. So this, as the Earth rotates, this sine theta changes, and we have done this also earlier, that this sine theta is nothing but omega e times t. That's the rotation of the Earth, angular rotation rate of the Earth. And so this is going to change. Okay. So as the Earth moves, this will also move along with it. And as a result, this fringe function will change. Okay. Fine. I will just stop here. This is an interesting concept. Just wanted to discuss it once more. And I will wait for your reaction. Any questions from your side? Students who joined? You can unmute yourself and let us know.
Good evening, sir.
Yes, please.
So basically, in a radio interferometer, instead of using one single large dish, we are using number of small antennas. So, are all these antennas are fully steerable? Like, can we use them to point any direction? Will it work as a single dish?
Yes, it will also act as a single dish. In fact, towards little bit later part of this, we will also come with different application of this antennas. Like it can also be phased up in the same direction as a single dish. All of them can look into the same. Instead of interfering the signals, correlating, we can also phase it up. That is also possible. So each of these antennas can act as a single dish, for sure. But what we do is we do the interference because, we interfere the signals, the cross-correlate the signals, because then we do gain in resolution, and we will treat you throughout this particular week's lecture. We will release it today. You will see that there is a lot of discussion of this. Before that, we wanted just to have a conversation between you and us to understand what we have done so far. So each of these dish are fully steerable. Well, for some antenna array, they are fully steerable. Like for GMRT, it is. For VLA, it is. But if you talk about certain other kind of arrays like SKA1, like LOFAR, for example, LOFAR has a completely different design. We showed you in the first slide, lectures, that it is a completely different design. It's called aperture array, and those are like we don't have physically steerable dishes, but we do steer the final primary beam electronically across the sky. Okay, so that's it.
Okay, sir.
Sir, I have a question, sir. Good
Please.
evening, sir.
Good evening.
If we observe using a single dish, an astronomical source such as an FR2 galaxy, we will see a blurred image because due to low resolution. Now, when we combine similar dishes into an interferometric array, we will still be seeing the same source. But I have a question about this imaging part. Each antenna will see that blurred output. So how can we combine these blurred outputs into a high resolution output? And how can we get fringes when we are observing some jet-like structure in every antenna?
Let me reconstruct your question, if I understood it correctly. So you're saying that you're looking at a FR2 source, right?
Yes.
So, okay. And then what was the question?
If we observe, each antenna can observe the FR2 source as a blurred jet, but we can resolve, that is, if we assume that each single antenna can resolve that FR2 structure, that is those two lobes, okay, then how can we get fringes, sir, when we observe them with interferometric array? That is, we are seeing two lobes like this structure in a single antenna. So when we combine multiple array antennas of the same parameters into an interferometric array, we will still get the same output but with higher resolution. So where do fringes come in this aspect, or how do the fringes appear with this particular shape?
Okay. Yeah. So okay. One conceptual error which you're making here is that for a single dish, okay, it has a single like radiation pattern, right? So for
Yes, sir.
it, this entire If it is supposedly, okay, I've drawn it wrongly. Let me just see if I can make it correct. So this makes an area in the sky like this, correct? Now, supposedly my entire FR2 is lying inside this, right?
Okay.
Then this will be looking as a single signal. So I will finally get a blob, right? I will get one amplitude for this location with a single dish, okay? Now,
Okay,
there are
sir.
ways to image with a single dish. How? Now, supposedly I make this dish bigger and bigger and bigger. Now we are going to draw things in not to scale, okay? Such that my beam becomes narrower, okay? Fine. That means
Okay, sir.
my footprint in the sky is like this much small. So then what I do, I take multiple pointing across this source. Understood? It's like a raster scan.
Okay.
Okay. And I then kind of create a map. However, each antenna will still be a single pixel camera. Okay. The only thing I'm changing is the field of view gets smaller, so I can keep scanning this entire thing with multiple raster pointing. Okay. Does it make sense?
Okay, sir.
So you have like you have your source. Let's do it in a proper way. And what you do is you kind of create a grid across this, right? And then you take your antenna to each of these cells and take one reading. Understood? So assuming
okay,
that
sir.
your each cell size is corresponding to antenna field of view. So your final pencil beam, I cannot draw, just a second. Your pencil beam now have this kind of a field of view. Understood? Remember, lambda over d is also field of view, correct? So we made the d larger so that it becomes narrower. And so I will just take it to one of the cells and keep taking the reading. So then I can I will not get this one, but I will probably get something like a blob, like a blobby structure, right? Something like this. Okay. For this one. Understood?
Okay, sir.
For a single dish. Now, when you do interferometry, what we are doing is we are cross-correlating both all the signals coming from n different antennas. Okay, I am getting n into n minus 1 divided by 2 number of fringes for each given time, right? So I am then collecting those and taking the Fourier transform of that, and that will be covered in this particular week. So stay tuned for this lecture. And then you will see the image appearing. So what basically happens is that, oops, sorry. Just a second. Yeah, can you see this again?
Yes, sir.
Yeah, sorry. So yeah, so for n number of antennas, you have n into n minus 1 by 2 number of baselines. Each baseline gives you one fringe. So you kind of have a superposition of that, and then do a Fourier transform to get into the image domain. If I fast forward a little bit, essentially what you get is something called a visibility, which is, if you take a Fourier transform of that, that will give you the sky image. Okay. That's what we're going to do. Now, in the sky, our typical coordinates are angular coordinates, and we typically define the sky coordinates in terms of L and M. So for the sky coordinates, we define them in L and M. So I is the image of the sky, and we define it as L and M. We will be look out for the lectures for more details. So LM are something, but they are called direction cosines. Okay, so how is it? It is linked as if you have done coordinate geometry, you have done it over there. It is L squared plus M squared plus N squared is equal to 1. That's the relationship which holds. That's the I, which is in the sky. So as you see the star or the radio star in the sky. Now that, if you Fourier transform it, that will give you something called V, which is the known as the visibility. And it is in a function of coordinates like U and V. Now it will look very Hebrew. Just hold on for a little bit. Okay. UV, so LM are the angular coordinates on the sky, and UV are the two of them are Fourier conjugate of each other. Now, how is this UV linked to the coordinates of X and Y and Z, which is kind of on the ground? We just show you one example, and we will not show you the derivation. So supposedly U, V, and W, things actually in the 3 dimension. This can be written as 1 over lambda of a matrix. I'm coming and writing the matrix up quickly. That into Xij, Yij, and Zij. I will define what these are. I will again come and define this matrix R very soon. This keeps happening to me. Sorry about that. Now, what is this matrix XYZ? This is nothing but we have seen the vector Bij, which is the distance between any 2 antenna is given by Bij. So I is one of the antenna, J is the other antenna. For a simple case, we took I as 1 and J as 2, which is also possible, correct? So for N is equal to 30, what will be the values taken by I? I can go from 1 to 30, and J can take values from 1 to Hi. No? Anyway, think about it. So this is nothing but the X, Y, and Z coordinates of the baseline. Okay. The distance between any two antennas. That's why I and J pair. And this R. So R metric we will write now. R is given by the first, it's a 3 by 3. So it's a 3 cross 3 metric. The first term is sine of H naught. What is H? H is nothing but the hour angle. So H naught is the hour angle. Okay, and delta naught is the declination for the center of the field. Given a frequency, my antenna produces a primary beam of some half power beam width, right? So when we're telling about looking towards the sky, we can point at multiple directions, right? This is looking at that towards the face, the field center. So sine of H naught, next element is sine. What's 1 second, sorry. This is a problem happens with a technical issue. Bear with me. Yeah, so we are back. So it's the first element. The second element is given by sine of delta 0, cosine of H naught. Third one is given by cosine of delta naught, sine of H naught. Then cosine of H naught, sine of delta naught, sine of H naught, and then minus cosine of delta naught, sine of H naught, 0, cosine of delta naught, and sine of delta naught. It looks a bit cumbersome, but all you have to know is that this matrix, which is like a rotation matrix, depends on hour angle and declination for the center of the field. That's all. But it's a very powerful matrix. Just let us dwell about it for a little bit more. And derive a very, very crucial concept. Yes. So look at this. U, V, and W is equal to 1 of lambda multiplied by some matrix, which is function of H naught and delta naught, and multiplied by this Xij, Yij, and Zij. So I'm not writing this matrix explicitly again because it's very cumbersome. It's simple. It's just purely based on geometry, nothing else. Now, the crucial concept comes now. These things are fixed, right? With the Earth rotation, this does not change. Lambda is fixed for a given wavelength of observation. It is fixed. Delta is also fixed right? But what is our angle? Our angle is nothing but RA naught minus LST. Now, LST is a function of time. So our angle is also becomes a function of time. What does it say? With the Earth rotation for the same pair of baseline, we will keep getting more and more number of U, V, and W. Okay. That means this particular feature that my both antennas were looking at the source in this manner, and then again the same source in a different direction as the source changes its position in the sky. My differential delay depends on B vector dot S, where S is the direction of the source. As this changes with time, this also changes for a fixed pair of baseline I and J, producing more number of these Fourier coordinates. So given a single baseline, just with the Earth's rotation, we are able to sample more and more number of UVW coordinates. We will come back to this concept again, but just for the time being, just to complete this concept, this is particularly called Earth rotation synthesis. Okay. So for a given pair of antenna, for a given baseline, you have more and more number of coverage in UVW, and that produces. So as you can complete this, as T increases, time increases, you get for a fixed Bij, you get more numbers of UV. Okay. So as you get more number of UV, you know this is the visibility we defined in UV, and that Fourier transforms to I. If you remember the Fourier, the sampling theorem, you need to sample in the Fourier plane at some rate, right, to be able to reconstruct the signal fully. We've done it in as Shannon-Nyquist sampling theorem. Similarly, we can take it by rule of thumb. The more number of UVW you cover, the better ILM you get. So to be able to reconstruct the sky image fully, the desire should be to cover and to sample the UV plane as much as possible. Okay, so that's the trick to interferometry. We will keep discussing this again and again. So I will again stop to ask GB Raghav Krishna for further questions.
So you are effectively saying that we need to increase the time of exposure to get better images.
Yes. So if you want to increase this UV, it is also known as UV coverage, and you will see in this week's lecture, we will discuss that. If you increase UV coverage, you get better images. Now, UV coverage can be increased multiple ways. The first one I told was by just increasing the time. As time is increased, you get more and more UVW for a given set of XYZ. Another feature is also if you can increase the number of lambda. So if you increase the bandwidth, that will have more frequency coverage, that is more lambda. That is also another way to increase the UV coverage. Okay.
But in that case, spectroscopy might be affected.
Which one?
Spectroscopic observations, because when we are increasing the bandwidth, a specific wavelength cannot be observed. So that is not, that can be observed, but it will be contaminated with our data from other wavelengths too. So will the spectroscopic observations be affected if we increase the bandwidth?
No, yeah. So basically, you were right. Basically, if you increase the amount of bandwidth, your spectroscopy will not be affected because your spectral lines also has a shape, right? It has a finite, if it's an absorption or an emission, right? It has a particular shape. So this shape translates to some delta nu, correct? Typically, you should be able to sample at a finer delta nu than that, right? To be able to reconstruct this particular spectral line. Okay. So that's okay. You can image for if you're doing spectral lines. You will not combine all the frequencies and make a single image. If you're looking at continuum, which is like varying very slowly as a function of frequency, then you will combine all the channels and make an image. Okay.
Okay, sir. Now I understand. And I have another question. Can you share sample question papers for preparing for the exam and also the slides?
Sorry, there's something in the background. I'm unable to hear you properly.
Can you share the sample question papers for preparing for the final exam, and also can you share the solutions of the assignments and the slides of the previous 7 weeks?
Solutions, yes. Solutions. Right. We are unable to share you the solution before they are due. Okay. So only after the due date is over, we will be sharing the solution. So Harsha, how many have been shared so far?
So far, we can share about 5 of the assignments because due date for us is completed, and we have shared the solution.
We haven't shared any of them.
We have shared, but we will share it once again. I think in one single file.
Okay. Also, can you share the sample question paper for preparing for the final exam?
You keep an eye on the assignments. Okay. All I can say is assignments will help.
Okay.
We are preparing the assignments in a way that it will help you to prepare you for the final exams anyway. But we will share more samples, and and keep an eye on the lectures, because we are after the last discussion session, we are included particularly paying attention to have at least one lecture in every week discussing about sample examples, right? So also keep a track of that. That will help.
Okay, sir.
Okay, great. Thanks. Anyone else?
Hello, sir. I just want to add one thing. So you spoke about half-hour beamwidth will be considered in the further explanation for the thing. I was just curious, like in a comparison between a dish antenna and other antennas, like wire antennas or anything, how the interferometry built with the Yagi-Uda or a log periodic would differ from a complete dish antenna. Will we be also looking up for that?
Yeah. So good question. Very good question at the outset. Let me try. Okay, maybe I don't have any other slides to support the drawing. You have to bear with my drawing, but apart from that, everything is fine. Supposedly, you have a Yagi-Uda or a lock periodic dipole antenna, right? Say you have multiple frequencies, correct? It has some amount of what we call D. Agreed? But this D is very, very much lesser than the dish antennas, large dishes, right? So the field of view is proportional to lambda by T. And if D is small, the field of view grows. So as D gets reduced, the field of view increases. So what happens is that we create an array of such. Let me just express this one, the log periodics, in this manner, the inverted V's. So what I do is that we have multiple such antennas. Say I can create a 3 by 3, and let this be called one tile. Okay. What I do is I phase up all the beams. I collect the signals from individual dipoles, and I collect it and phase it up to create a single beam response from one tile. This is then called a tile beam.
Sir, I would agree with this. So you'll use the array antenna to reduce the beam width and equate it to the dish antenna at lower frequency.
So but now this becomes your dish.
Yes.
Okay, where this dish is much higher than the other D, and so you have a reasonable size. Because for a single dipole, your the beam is like horizon to horizon, right? It spreads over the entire.
Yes, somewhere like, 30 degree by 40 degree, something like that, 30,
exactly,
20 degree.
exactly. Yeah.
So you would say the interferometry built with only such two elements would not result in any of the observation results? So, like
no, I'm not saying that. I mean, see, depending on your science case. Okay. Supposedly you need to have a brid, you're relating a very strong event across the sky. Only you need to have a signal. Correct? Then that is fine. Okay. But also you have to understand that this increasing capital D also increases as a result the effective antenna area, right? So each of your tiles are more sensitive than a single dipole, because the area, ultimately the area also increases. So the amount of signal you're collecting also increases. Sensitivity increases as you move from a single dipole to a tile of dipoles. Okay.
Okay.
So it's not just about the field of view that helps, because at the moment you have an unwanted large beam, you pick up a lot of spurious sources, lots of things which you do not want to see.
Okay. My question was, I have a large antenna, but I'm spacing them 10 kilometers apart or something, so that the fringe would become very small. So at that time, my resolution would increase. That was what my thought process was.
No, yeah. So given there's a little bit of a catch, let me tell you. So supposedly you have, let me just take this up. You have a 1Y, right? So the maximum distance between these two is, say, 10 kilometers, right? You have many antennas over here. Now you have one or two which are placed 100 kilometers away.
Okay.
Right. So this is also a structure of something called, if it is also there, it's called a VLBA, very long baseline array, where you use the VLA but also you use the other similar dishes across the continental US and creates 1,000-kilometer baselines. Okay, but now let's see what happens. So you have about 351 baselines from the VLA and the 27 baselines with this one antenna. Okay, so and then so even though I said that lambda over B max is the resolution, but also the distribution of the baseline matters as well. Do you understand what I'm saying?
V by U coverage.
U by V coverage, correct. So how these baselines are distributed across the length. So supposedly, if I draw this, say as a function of baseline length, so modulus of that, and then total number of baselines, right? Then I definitely will have at a lower value much larger, and then at like something like this, a tapering function. But supposedly I have this and then very, very low and very few baselines. So typically that won't add too much of sensitivity. So we need to have a good, healthy distribution of even longer baselines, shorter baselines. We understand the shorter baseline has to be in large numbers and so on and so forth. We'll come to this a little bit later. So you can do, so what was actually originally your question?
So that is what, like if I have any Yagi-Uda antennas, 2 elements, I want to do only 2-element interferometry. Can I reach to a resolution of a 10-meter dish antenna or 5-meter dish antenna, something like that? So
ideally you can, because if you just place it by that much of distance, you are essentially having a fringe which will detect that kind of a source. So I think we did this. We are doing this in this week. That can I just yeah, I read it. Okay, not still. Just a second. Let me add a blank slide and yeah. So I think you can do. Supposedly you have a one extended source like this, right? If you do a Fourier transform of that, you kind of in the visibility you kind of get a function which is like a Gaussian function. Okay. If you have a smaller source, like a little bit smaller source, then that will give you a Gaussian with a little bit weaker, yeah, and so and so. So if you have 2 Gaussian sources separated by something, you can also have a response like that. So what I'm saying is, by looking at the visibility function, you can determine the shape of the object also. So ideally you can, but whether we will be using, we will be able to beat the signal to noise. Because remember, every visibility also will come with its own share of noise. So that's another trick. But ideally, yes. Okay.
okay. Thank you, sir.
Sir, excuse me, sir. Based on the last point you said, I have another question. May I ask it?
Please.
By looking at the shape of the visibility function, we can determine. You said we can determine the structure of the source. But when it comes to CMB mapping, how does this help?
It does actually. So if you look at the visibility, is a good point. I mean, we are now jumping across. We will put into the slides when we discuss science. So you can measure something called a power spectrum, okay, and in the visibility domain. So you actually okay. So let us look into this purely from the point of view of the Fourier transform. ILM and VUV are Fourier pairs. So LM is in the angular coordinate. So this is the angular kind of the width of the thing. Fine. This is inverse of that, right? That means you're talking about inverse relationship. And so supposedly you are looking at something at the very large scales that will automatically lead to looking at large angular scales, right? That means that is coming from a very lower or higher values of U. So that's how the lengths are related between the UV and the LM. So in CMB or any large scale structures, you're essentially looking for a very very large angular scales of the signals, and that's related to the UV W values. Okay, so we will link those clearly. So in a real space, R is nothing but yeah, let's not go there right now. It will confuse us more. But yes, I mean, you can detect structures at different scales. So to answer your question, we can do that. Stay tuned a little bit later towards the end of the course when we discuss different kind of science usage. We will come back to that. Make sense? just hold.
Okay, sir.
We were jumping too much. Anything else? Diptangshu.
Will there be another live session, sir?
Sorry?
Will there be another live session after this?
Another?
Will there be another live session after this?
Yeah. I think we can have one per week till the last week. I mean, this will be useful to come back and get feedbacks and discuss live. And we'll set it up. No problem. Every week we have one. Let us see. There's some chat. Okay.
Excuse me, sir.
Please.
Sir, will this video be uploaded today, sir?
That I have to ask the team.
Okay, sir.
Let me just. You missed some of them earlier.
Sir, I didn't miss actually, sir, but I prefer to watch it 2 times only. Then I can grasp everything properly, sir.
Are you being able to follow what is happening in the class? Any questions?
Sir, better than before, sir. I started referring to the Griffith's book for electrodynamics, sir. So now I'm able to understand better. But I think I
we
need
have also a
one
little bit rearranged. We are paying a lot of time to revisit the examples more thoroughly. Examples not only for this week's lecture, but also covering a bit more from the previous week's lectures. So that we are doing. So we will be happy to have one sessions lives every week from now, if it can help for you.
Yes, sir. It helps a lot, sir.
If you want to discuss any particular topic, please let us know early enough so that we can come prepared for that.
Sure,
if
sir.
possible, you can drop a message in the discussion forum, right, Harsha? Yeah, please,
Yes,
please drop it, and we can take a note and come back. So I can announce today only. Next week we will just check the schedule and understand when will it be, but most likely Wednesday or around Wednesday, maybe Tuesday or Thursday, but not Thursday. Wednesday probably preferred, but let me see if there's any holiday or any other issues and conflict. we will announce it probably by Monday. So stay tuned here. Anything you want to discuss, please let us know early. Raghav Krishna or who was the other one? Akshay or anybody else. I mean, just there's a lot of students. You'll be happy to reach out. Anyone else? Last 7 weeks, share the slides. Slides are shared, right? Ravi, who is Ravi?
Hello, sir. Will it be
Slides are
possible
not
to
shared?
share the slides which you?
So slides should be shared, right? No?
No, we have no access to the slides.
Oh my God.
In the sense, we can see the video, but we don't have the slides.
Sir, none of the study materials has been uploaded. Means we have to see something to that.
Oh, that is not because we have been supplying them. So okay, we'll make it a note. I don't see. I don't think anybody's around to tackle this. I see there's a login by somebody from NPTEL, but yeah, we have shared. Sorry to just to put it on record. We have shared our materials for every class. Extremely sorry for that. Please write also to the discussion forum. Okay, and we will get reminded again.
Sure, sir. Thank you.
Sir, if I may suggest, is it possible to create some WhatsApp group or Telegram group so that you can easily share the slides there?
I couldn't get it. Sorry. Yes, can you come again once more?
Is it possible to create a WhatsApp group or a Telegram group so that it will be easy to share the slides and solutions directly to us?
No. I mean, I think there are ways to do it. Let us try once, and before we come back next week, if it is not sorted out, then we can discuss the alternate ways. But we'll follow up with the team, and they're fantastic. They help us quite a lot, and so we will just see. I mean, there are definitely ways, and we'll just see that, and if not, then we'll think about these alternate ways. Okay.
Okay, sir.
Great. I mean, if not, there will be something like a Google Drive or something. You can download everything from there. That's also possible. Okay. If not, I have my own web page. If we can also put it there, that's also fine. But let us see. Let us see how it is. Why it is not done. Okay. So Harsha, can you just make a note of this?
Yes.
Thanks.
Right.
Any other questions? Otherwise, I see we have almost used one and a half hour. If there are any other questions, we can continue. And so, yeah, one thing which came out of this questions regarding the direction, as we discussed, just to finish on this one. Yeah. So see this particular. So when we had this concept, you can see the slide, right? So, yeah. When we had this concept, so for a given frequency, the antenna has a half power beamwidth. So towards the field center, only what we are discussing, the direction of the hour angle and delta. However, there are other locations inside the field of view also, which matters. So for this part, we are only looking towards the field center. So as if only one direction for a given antenna. Okay. Remember this because this is very crucial. We'll come back to this as we progress. So this entire thing, interferometry, is centered around towards the field center. We will also make it note as a phase center. And why so? Watch out for next few lectures. Okay. Any other questions? Please don't feel shy. This is a session for all of you to bring up questions, and any question is a good question. Don't be shy and don't stop asking, because you never know which one is a better question. Sangeeta, on the one? All okay?
Hello.
Hello? Okay, some issues. Yeah, I'm unable to hear you. Harsha, can you hear her?
No, sir.
Who else is there? Brenda?
Yes, for now, I don't have any questions now, sir.
Thank you for joining us.
Yes, sir.
Nidhi Kumar?
No, sir. I don't have any question for now.
Everything okay? Working out fine? That the assignments make sense? Are you able to catch up with everything? Any difficulty? Anywhere we want to again revisit the particular thing? Whatever you want to have help for, we are here. Shreya?
Hello. Yes, sir. Yes, sir, there are no issues. Sometimes I find it a bit hard, but yes, that's because there is some many new things which I am encountering for the first time. So, yes,
Okay.
otherwise, it's good.
Any particular area where you feel particularly it is steep?
No, sir, not in any particular area. Previously, I found it very fast, but yeah, from fast 1 week and 2 weeks, it
Yeah.
is the pace is good. So I am able to.
Right. So we did a bit of calibration after that first
Right.
discussion, and we thought of little bit slowing down, not at the extent of the content, but I mean we are covering the same content, but little bit reorganize it so that it becomes easier for you to handle.
Yes, sir. Yes, sir.
And we are also going to tell that what part is for if you're sitting for the exams, what is the minimum you have to cover henceforth,
Yes, that
and
is.
what is just there for just the completeness. Because some people, as you are saying from the discussion itself, some people are coming to learn a little bit more, and some people are catching up. So we are trying to help everybody. Okay, at least trying. Maybe we will not be able to possible, but try to somewhere in the middle is better. Yeah.
Sure, sir.
Great. Thanks.
Sir,
Anyway,
I had one doubt, sir.
please.
Sir, in assignment 6.1, sir, the last question, a parabolic reflector antenna has a diameter of 4 meters and an operating frequency of 20 gigahertz. Calculate its aperture area in square meters, sir. So, sir, I found a way where they found the area of the antenna and they were trying to fit it into a parabolic model, sir. So, do we need to do it that way, or just pi r square is enough, sir?
I mean, that's okay. I think just doing, I mean, that the TA is here, he may be able to answer it better. For me, of the order of is okay. Harsha, that's the understanding, right? You said it.
Yeah. So means basically when you design any dish, you first go on to approximations. Then when you are going towards facing a science problem, then you do those things in detail, means fitting curves and all those things.
Okay, sir. Thank you for explaining, sir.
Thanks, Ravi.
Hello, sir. One thing I noticed on the NPTEL website is it is mentioned that we can submit our results multiple times, but I noticed in one of the assignments it was not recorded properly and my scores went down because although I had changed it, it was not evaluated for the latest results I posted. So it will be nice if you could tell NPTEL somehow that these multiple records are missing.
This is called something called re-evaluation, I guess. Sorry, I'm catching up with the NPTEL procedures. I think we'll take it up. If you just can drop my email ID is there. If you can just drop me an exact problem in which assignment,
Sure.
we will try to take it up with them and see if a resolution can be
Sure, sir. Thank you.
Okay, but it has to be based on their terms and conditions and rules.
Definitely.
But if there is a possibility, we will definitely help.
Sure, sir. Thank you.
I had a similar problem. I submitted the 4th week assignment at 11:57 p.m. So it did not get accepted. But the due date is actually 11:59 p.m. So is it possible to do something?
You again, when you do the same way, just write to me with the exact thing. Please, in the subject when you're writing, or you can write in the discussion forum as well. Harsha will pick it up. We'll pick it up and we'll comment. No issue.
Okay, bro.
Any other? Okay. If not, then I think thanks a lot for Harsha. Do you have anything? Any quick thing to just go over?
Yes, sir, I had, but it will take time. But okay, so just to show you a bit, if I am able to.
Yeah, just let me stop sharing. Yeah, go ahead.
Sure, sir. So, this is kind of I compiled all the assignments answer into one particular slide. So as everyone was asking and suggesting to provide stepwise how to solve for an answer. So this contains every steps and whatever we have provided as a PDF to the NPTEL. Each and every step has been followed. Means like whatever the typos and everything was there on the configured on the website. So that all means there is actually kind of one week bar period for us. Means even if there is a typo in the configured assignment, which we are able to see later on. So after the assignment is submitted, there is a one week of time. So after that, the correction will happen. But it will be very helpful if you like till now you are pointing out what were the problems you are facing. That is very helpful to us. So this we will try to communicate with the NPTEL and you will get it for sure. Means everything, whatever the necessary formulas are there and how we are calculating it, everything is mentioned here in this particular slides. Okay, so this was I was gonna this was in the line to discuss, but we can discuss it over the next meeting.
How long will it take? Half an hour? Maybe we can finish.
Sir, there is actually 6 assignments.
I see. So is it then possible just maybe we can record and then post it so that they can just go over anyway?
Sure, sir. Sure. I will do that.
Yeah. Okay. So what for your benefit, what we'll do is that because we have only I think for 3 or 4 weeks left, 4 or 5 weeks left for this particular course. I think we'll not use up the live discussion, but what we'll do, we'll post it as an additional material, and this particular discussion which Harsha was referring to, and which is very vital and probably help you a lot. It will be posted under the additional material section, and then you can go through it and come back with more questions next week. Okay. So great. Thanks a lot for joining us today, and hope you have a good week ahead, and we'll see you sometime next week. We will check out for the announcement. Okay. Thank you.